difícil. É isso mesmo. São 40 minutos, né? Pensei que era 50.
Okay. Okay, so let me start. Just before I start the next talk, I would like to mention that we have coffee break after this talk. It's just serving in the corridor hall. So we have 30 minutes of coffee break before starting the next talk. Okay, I am pleased to announce another speaker. He is Zaqueu Ramos from the Federal University of Sergipe. He is going to talk about the Janeiro transformations in arbitrary dimension and ideal theoretic view. Thank you very much.
Thank you, Maral. I'd like to thank the organizers for inviting me. It's a pleasure to be here. So this talk is about the Janeiro transformations in arbitrary dimension. This is a joint work with the Professor Semes. Okay. To start, I introduce the Não está movendo.
Melhor você mover daí, pode? Faz um teste.
Ah.
Mover um pouco.
Ah. So K is an infinite field, okay? R is a polynomial ring over K. F0 to Fm are linearly independent homogeneous polynomials of the same degree D, such that the GCD is equal 1. And I is the ideal generated by F0 to Fm. And the F is the rational map defined by the polynomials F's. Related to the ideal Y, we can consider there is algebra. This algebra, we can see this algebra as a bigraded K algebra generated by the variables X and the polynomials F0t to Fmt. Geometrically, this algebra corresponds to the bihomogeneous coordinate ring of the graph of F. Okay. The dimension of this algebra is the dimension of the ring, the base ring, plus 1. Okay. If you make the bidegree of the variables x equal 1, 0, and the bidegree of the variables y equals 0, 1, 0, 1, and the bidegree of the variable t equal minus d 1, we have that this epimorphism is bihomogeneous. In particular, the kernel is a bihomogeneous ideal. We call the equations of a minimal set of generators of a Q of implicitly defined equations of the Riesz algebra of I. It's a fundamental problem to find the implicit equations, defined equations of the Riesz algebra. This problem has been studied extensively by commutative algebraicists, algebraic geometers, and more recently by applied mathematicians in geometric modeling. A complete solution requires that one begins with knowledge of the structure of the ideal I. Some ideals, where these equations, the implicitly defined equations are students, are perfect ideals of codimension 2, determinantal ideals of arbitrary size, Gorenstein ideals of height 3. Okay. Some implicit equations arise from a free presentation of I. If you have a free presentation, it's easy to see that this ideal generated, como é que faz para mim? This notation means the ideal generated by the entries of this product. Okay. Hence, this simplest situation is when this inclusion is an equality. Okay. In this case, we call the ideal of an ideal of linear type. Linear type is a very restrictive condition. For example, this condition implies that the minimal number of generators of I locally in P is at most the height of the ideal P for every P in VI. Okay? This is the G infinity condition. And this implication, the reciprocal of this implication is true in this situation, right? When I is an ideal in the linkage class of a complete intersection. Sims and collaborators have investigated how the implicit equations of the Riesz algebra affect the birationality of F and vice versa. In this talk, we will consider this type of equation in the context of generalized de Jonquière transformations. Plane de Jonquière transformations are classically well known. Besides that simplicity, a mid-order plane Cremona transformation, they constitute the essential tool in Castelnuovo version of Neto theorem on the generation of the plane Cremona group. Recall that a birational map of P2 has homoloidal type, the M1 to MR, if the linear system of F, which is given by the set of curves or equations, like this, has base points P1 to PR of multiplicities M1 to MR. By base points, we include infinitely linear points, base points. A de Jonquière map is a birational map with this homoloidal type. We have the following characterization for the Jonquière, for the one when a birational map is a de Jonquière map. Okay. Then F is a de Jonquière map if only if up to project coordinate change, source and target, is defined by the forms fx0, fx1, g, such that fg are relatively prime monoids on which has degree 1 and in the variable x2. Monoid is a polynomial. It means a polynomial of the shape P key where P and Q.
To have degree at least one, it doesn't mean that B is not zero.
Yes. Yes. No. P can be zero. Okay. He.
One of them.
Yes. The definition of the Jonquière transformation for arbitrary dimension takes into account condition B of the above characterization. An explicit description for such a transformation was given by Van Pan in 2001 under the designation of transformation stellaris. Okay? To introduce the generalization of the Jonquière map, let G0 to Gn minus 1 homogeneous polynomials of the same degree D in the polynomial ring in these variables, okay? In n variables. And consider F and G forms of degree D minus D prime and D respectively, such that the GCD is equal 1. In this case, we have the following, this proposition, okay? The rational map with these coordinate functions is a Cremona map of Pn if and only if the rational map in Pn minus 1 given by with coordinate functions G0 to Gn minus 1 is a Cremona map, and the F and G are Xn monoids, at least one of which involve Xn effectively. Okay? With this proposition, we have the definition of generalized de Jonquière transformations, okay? And our goal is find the implicit defined equations of the Riesz algebra of the base ideal I generated the base ideal of the Jonquière map, and they characterize when the Riesz algebra of I is Cohen-Macaulay. To identify for the implicit equations of the Riesz algebra, in addition to the equations that arise of decision matrices, one uses the fully downgraded sequences. To introduce the fully downgraded sequences, we consider 8, 0 to 8n minus 1 forms of the same degree, the frac, define the inverse map of G. Remember, G is the rational map, is the Cremona map defined by the support, the Cremona support, okay, of the Jonquière map. And then we consider 8, 0 to 8n minus 1 forms of the same degree, define the inverse map of the inverse of G, and the delta, the corresponding source inversion of inverse factor. That is this form that satisfies this equality. okay? And consider Z a syzygy of the base ideal of degree whose the last coordinate is non-zero. And the delta, the last integer such that the coordinates of Z is contained in this ideal, in this power. Then we consider this form, okay? In particular, this is a form in the presentation ideal of the Rees algebra of the ideal I, okay? And if delta is bigger than 1, we can rewrite F1 in this form. Okay. Where F1y are bihomogeneous polynomials in this power. And now we define a new biform, F2, okay? Then if you evaluate F2 in the forms FGG, and you remember that the H0 to Fn minus 1 are the forms that define the inverse of G, we have this equality. De novo. Tem, que é quando aperto no meio. We have, in particular, since F1 belongs to the ideal, to the presentation ideal of the Rees algebra, we have this equality. Thus, the biform F2 is also a polynomial in the presentation ideal of the Rees algebra. Now, of biform of by degree e minus 1, okay? And we repeat this argument for F2, okay? Então, if the delta is bigger than 2, we can rewrite F2 in this form, okay? And construct a new biform in the presentation ideal of the Rees algebra. We iterated this process until we get F delta plus 1. And the sequence of the biforms Fi, we call a fully downgraded sequences associated to the syzygy Z. And now we consider this particular case when the support Cremona of the Jonquière map is the identity. In this case, we can prove that this is the minimal resolution of the ideal I, where the syzygy matrix Psi has this form, okay, where this submatrix K is denoting the physical zoom matrix of this regular sequence, okay, and the G is given by this equality here. And the detail the n minus 2 tail terms are the n minus 2 tail terms of the Quoos complex of this regular sequence. And in this case, we can, to prove if you let Z be the last column of Psi, and the Fi, the fully downgraded sequence associated to the CZG Z, then we can to prove this result, okay? We can to prove that the presentation ideal of the Rees algebra of the base idea of the Jonquière map is this. And the idea of the proof is the following. By the resolution of R, we have that the depth of the R module I is positive. In particular, there is a linear form, L, that is R module I regular, and with, we specialize the ideal I, module the linear form L. In particular, the CZG matrix of I is a CZG matrix of I tilde. The implicit equations of the Rees algebra of I tilde are known by a result of Benítez and D'Andrea. And through the implicit equation of the Rees algebra of I tilde and some calculations, we obtain by lifting the desired equality, this equality here. And now we stud the depth of the Rees algebra. For this, we consider this sequence of sub-ideals of the presentation idea of the Rees algebra. Okay. A fundamental result is this lemma. Okay. With this lemma, we can to prove, since the ideal I, we can see the ideal generated by the entries of the product Y times K, we can see this ideal as the minimal, the ideal generated by the two minimums of this generic matrix, okay? But the ideal generated by this, but the resolution, the free resolution of this ideal is given by the Eagle-Northcott complex. And the ideal generated by the regular sequence is resolved by the Quoos complex. We can use this and this sequence, this exact sequence, to construct a free resolution of Q of length at most n plus 1. In particular, we can deduce that by Ausland Book's formula that the project that this theorem, okay, that the Rees algebra is almost Cohen-Macaulay. That is, the almost Cohen-Macaulay. It means that the depth of the Rees algebra of I is at least the dimension minus 1. Okay. And we conjecture that the Rees algebra is Cohen-Macaulay if and only if né? The degree of the forms is at most the number of variables, okay? And this.